Today's session mostly will be dedicated to networking, to data transmission networks, and somewhere closer to the end, in second part of today's session, I will also add more details about previous exercise because I ran out of time and was not so well prepared to show how, at least in theory or in not so good practice, you could complete homework, what I described previously. So for new theoretical part, agenda is to introduce you into data transmission networks. I will try to explain basic principles how data transmission networks work, and then we will go in a little bit more details what Ethernet is, what wide area networks are, and a little bit about used protocols like TCP/IP, DHCP, DNS, and ICMP. So, what are basics of networking? Networks are used to send information, and to send information you have to encode this information into signals, and any change you can transmit through some media like risen flag or lowered flag or explosion of cannon or whatever might be used to transmit just one single bit of information. When you need to transmit something more, not only like new king is born or old king is dead or whatever, then of course you need to agree about some schema how you encode more than single bit of information. And when you need to encode more than single bit of information, you just need to remember that everything can be described just as a number. Every number can be represented as a binary code. So this means if you need to transmit something more from place to place, you need to transmit more bits from place to place. And particularly for networks, you first need to have established some medium where this signal will be traveling through. And we already have different kind of networks like transport network, like old school wired telecommunication network, like power, electricity transmission networks, etc. But in this lecture, of course, we will not talk about these other kinds of networks, and there are quite a lot of similarities between these networks and dissimilarities as well, or differences. But we will talk about data transmission networks. And the important thing to understand is that when many nodes or devices and people are connected to the network, you somehow need to manage traffic generated by these messages sent from one particular node to another particular node. And initially, data transmission networks evolved from telephony networks where you transmitted voice encoded into changed electricity. So initially, data transmission networks were no such a thing, so we still used established voice communication networks like phone networks to transmit data. And for voice communication networks, the idea was that to transmit your voice from place to place, you need to have some junction box where you had to connect and disconnect particular paths for this DC and AC, or direct current and accelerated current, from phone to phone to establish this contact. So, and old school telecommunication networks were circuit switching networks. So if you wanted to send voice from telephone somewhere here to telephone somewhere here, you had to establish actual current path for this accelerated current to go through these particular wires or cables. And the good thing about such approach is that you can always guarantee some kind of minimum service, that if this connection is established, you will be able to communicate. Not so good thing is that you need to wait in queue. For example, you can't get free switch to prepare your circuit from one place to another if this box here is busy. So either you good, quite guaranteed quality of service, or you need to wait in queue. And also what is important is that when these phone networks become more and more complicated, and so when you use accelerated current or changing electricity to send information or bits or voice, changed voice through these wires, what actually is traveling is electromagnetic waves are traveling through these cables and wires, which causes disturbance in electron flow or in electricity flow. But if you know something about electricity and electromagnetic waves, you should know that there are different electromagnetic waves depending on how you what their frequency is. And for more complicated telecommunication networks, you actually could send signals for more than one channel during time, doing it in a following way, that either you switch sending voice signal in small amounts of time. It's like time division. It's something like how you make concurrent support for multi-users and multitasking systems for operating system. So instead of sending only one signal about only one connection and conversation through the wires, you actually are sending many of them for small amount of time. So sound spectrum is something like 20 Hz to 20 kHz, but particularly in phone conversation network it is cut to approximately 8 kHz. Therefore, voice through the phone is always not so bright. And if you do this multiplexing much more times than you send another conversation, nobody notices anything. For example, when we switched from analog to digital connections, during time it happened like this. So if we send information from about voice from what is lower, like 80 till to 8 kHz of voice, so during time this means we have to send changing voice for particular conversation at least let's say about this speed. Actually it's till to 4 kHz. So this is one conversation sent about voice modulation during one particular time. But if you can actually send much faster changing signals through it, you can send another conversation in other time, and then another conversation in another time, and that is this time multiplexing. So, and then you pick up only these time signals, which depends and belongs only to one particular conversation at the end, and you can use the same cable or wire to send more than one conversation at that time. That's one thing, how can you do this. Other thing is that it's not so easy with electricity, because filtering out particular wavelengths for electricity or particular spectrum is a little bit harder than for light. But you can also do in different way. So if you have many conversations going and sending through the different signals through the time, you can pick up some signal in one regular time and some signal with different time, which is either more frequent or less frequent. And if this frequency is good enough to not lose quality, then you can filter out this lower frequency signal and for one conversation and higher frequency signal for other conversation. For accelerated current, it is quite complicated way to do, but this works very well for optical networks, because light is much easier to handle and to pick up particular wavelengths and to see. So in old school approach, when we switched from fully analog communication networks to digital networks, they usually did this time division, multiplexing, but in more modern networks, especially if optical cables are used, in most of cases this frequency division multiplexing is done, so that we are using different wavelengths to send concurrent parallel signals through the same medium. And so that's how this multiplexion and demultiplexion works if it is done in time division. So you have much higher frequency or shorter times when you send signals than you have for each particular separated line, and then you send them in particular order. And when these time slots are all full, then of course you can't get more concurrent conversations or data transmissions during that time. But particularly for data networks, later another approach was introduced, which is leading approach today, how to transmit signals or data from one place to another. An idea here is following, that there is no established and guaranteed circuits from one place to another. These circuits are virtual, or these are called routes, not circuits anymore. And similarly as this time division multiplexing, data are sent in small chunks called packets. And then these boxes here, which previously created either actual or virtual circuits in between, they are now established circuits, but only routes where one particular chunk should be sent from one place to another. And what is good thing about this approach is that it is much more robust, because if there is possibility to send some chunk of information from place to place at all, then you always can get some kind of connectivity Only thing is that as more busy this box becomes, as less data you can actually send through. So when this box is not busy, any new chunk of data sent in its input can be provided into output. And of course, this box becomes a little bit more complicated because most of these boxes work in such a way that they read particular chunk into buffer and then retransmit this chunk of data from buffer to another circuit. So it needs some internal memory. In difference with such approach, it still needs to have memory to create these connections, but this memory can be implemented in much easier way just by using algorithms to describe these switching criteria. And so, one bad thing about such approach is that there is no absolute guarantees about sending data from place to place, because any box in between you and as a sender and some receiver, some of these boxes may be busy and some of these small chunks or data packets may be actually lost. But practice has shown that this approach works much better, and this idea was established when internet was developed. And first thing how internet was developed is that it should endure nuclear holocaust when USA and Soviet Union just bombs both countries with nuclear weapons, but governments in USA still should be able to communicate each to other using some reserved roads or whatever. And so what is important about packet switching? Important part about packet switching is that if you have circuit switching, only thing you need to send is just dumb data, current numbers about your voice levels, current numbers for your computer modem, what you want to send, receive, and that's it. But if you start using packet switching, then besides data themselves, you need to send additional information, because packet here is something like individual car on traffic. So packet itself should know from where it is going to where it is traveling. And so to make each packet like individual car going through the roads, each of these cars should remember what they are doing. So that is additional overhead for data. So you always need to add some header which says this packet is going from here to here. So that is overhead, but it is good overhead because then if some of packets is lost, then only some packet is lost, not entire communication, because each of these packets may be sent through the packet switched network independently. And probably if you will go in more details studying information technologies and you will study in deeper level data transmission and communication networks, sooner or later you will see picture something like this. And this picture is developed by a consortium called Open System Interconnection, which describes how internet is working. And what this picture shows, on left part it shows one device which is using internet protocol, and on right side it is showing another device which is using internet protocol as well. Here there are 7 abstraction layers how you can look on data which are transmitted from one side to another side. And if you look on high abstraction layer, and we will look on high abstraction layer as well, you can ignore everything else beneath it as a foundation of it, and you may talk about things like web client or web browser is communicating with web server. That would be this application layer, like how web browser requests data from web server and how web server responds back. But what is actually happening is that they do not communicate directly. When web server sends data or web browser sends data to web server, what actually is happening is that they are layer of protocol drivers and device drivers, and web browser sends this data to protocol drivers for operating system, and then these data are encapsulated and put in proper order or whatever until they reaches lower level here through device drivers, when these data are converted from actual data into signals encoded by these bits of data, and only then actual signal is sent from one device to another, and this signal is received in physical hardware, in network card. Then these signals are converted into bits, and then these bits are grouped depending on what kind of intermediate protocol here is used, and only at the end operating system somewhere here provides this data to web server, and web server sends it back. So computer scientists and this consortium described this as 7 layers of abstraction. In practice, if you are using Internet Protocol and your network is based on Ethernet approach, that means either wired Ethernet or Wi-Fi or Bluetooth, and even USB is similar, or FireWire. All principles here are very similar to Ethernet network. Then you actually need to remember only approximately 4 layers from these 7 layers. And if you are using Ethernet network, then you have Ethernet card in one end, Ethernet card in another end, and wired network here, or Wi-Fi card here, and just air between them, because then in Wi-Fi network signal is radio waves, in wired network signal is small accelerated current through these wires. And then in this Ethernet card you have data which are needed to send these chunks of data from one Ethernet card to another Ethernet card, and particularly for Ethernet, Wi-Fi, USB, Bluetooth, and similar networks. Important part about Ethernet is that each of these devices have globally unique address, and therefore you always know which device is sending data to which device, because address system is already established by manufacturers of these devices. And then everything else from Ethernet perspective is just data. But if these data are regarding to Internet Protocol, then you need also to say what IP address has this device and what IP address has this device. And then also port number on this device and that device. And then if it's also reliable data connection like TCP packet, it also counts how much data were sent from one device to another device, how much data are received, and then everything else is data. And for example here, if it's web browser and web server, web browser may send something like getindex.html to the server. So how does it look in demonstration? So one of leading applications for debugging networks and understanding how they work is called Wireshark. And Wireshark also may be used to debug USB networks, because USB is similar to the Ethernet, but in this particular case we will be checking what happens inside our network, and I can start writing something with this application. I did something into network, like open this web page. I actually wanted to open something like this, but it doesn't matter. And what I have recorded here, I have recorded bits sent and received through the network card of this virtual machine. And in general it is just stream of bits, but this stream of bits has internal structure. And therefore we can aggregate this internal structure on more easily ways to handle. And first thing to see here is that because I'm using Ethernet network, what I'm actually sending, I send small chunks of information called Ethernet frames from this machine to something else. I will tell in detail that it is actually a router in local area network, because this website odo.lv of course is not reachable locally, so it needs to be sent forward using internet. And what we see here is that first part here, this green data, or if we look on all data as a stream of bits, that dark green part about Ethernet. So what we see here, that Ethernet frame was sent from this device, and here it says something like how long this chunk of information was, and here it says from which Ethernet device to which Ethernet device these data were sent. So so-called media access control address, or MAC address in short, of this machine is in hexadecimal 52, 54, 00, 12, 35, 03. That's destination. And source is this one in hexadecimal. And type is this one. I don't know much about type here. So this is this header which told this device is sending Ethernet frame to that device, actually vice versa, this device to that device. Length of send data is 808 bits. And then everything else from Ethernet point of view is just internal data. But this internal data also has some structure. And if you are using Internet Protocol, then important part about Internet Protocol is that it also has addressing system from device to device. And in this case, source address for this device is 10.0.2.15, destination address is 10.0.2.3, and then some data here. But because these data here are UDP protocol, we see here additional data like source port number and destination port number, and then actual data here, which we will look in details later. So it's domain name system query. So it requested what is incoming.telemetry.mozilla.org. Oh, that's interesting. Shouldn't be such queries here. So some telemetry data are sent here with this browser. So that means I believe because of this, and here. And similarly to other packets here. So that's how this looks, particularly for Ethernet. So then, Internet is consisting of many sub-networks connected together, and so you can create network of networks in different ways. And initially there were different kind of networks used, namely bus, and we talked about computer bus already. So what is important about bus is that each devices share the same medium to send data. And of course for networks it is serial bus. And initially, particularly Ethernet network was used with coaxial cables, like for TV sets. And so each device is connected to Ethernet has T-junctions connected from this bus to another device, and because of wave reflection at the end of these devices, at the end you had specific terminators which heated up this reflected wave of electricity at the end. And what is good about this bus network is that you don't need to have too much of materials, because you can just use one single cable here to go through very large buildings, and so total amount of materials needed is not so big. What is not so good is that if this bus is quite busy, then you have congestions, because only one particular device may transmit these chunks of data or Ethernet frames, and only one is intended receiver. But of course the signal is received to all other devices. Only all other devices are ignoring this signal because they see that their own MAC address is different than destination MAC address for this target destination. So on any time you break this cable here, big part of, actually all part of this network may be broken, because then its wave resistance is different, and so you have noisy network and nothing works. So therefore later IBM introduced a star network which is called ring, because in this star these devices are not talking everybody with everybody, but there is retransmitted so-called ceļojošais karogs, traveling flag from device to device, and only this device which has received this flag is allowed to transmit something. So when previous device says, okay, I'm giving this flag to you, and flag is just specific chunk of data sent through the network, then next device is sending. So good thing about such is that in star topology, if something is broken here in network, usually not entire network is down. Not so good is that of course you'll need much more cables here, because if you have just one central hub here, then all cables going to particular computer are much longer. And good thing about this ring topology or talking passing, like plug passing who is talking, is good from congestion's perspective, because if some of these devices have nothing to say, they just give this token to the next device, but this token may be lost and it needs to be created by some more equal nodes than other nodes if there is no token passing through these networks. So an entire system, how it works, is more complicated, and therefore such approach of network is not widely used anymore. And today's network topology, which is most widely used, is star network without tokens. That means that you have central devices where many cables are connected together, and if everybody is allowed to shout out some signal anytime they like, but before they shout out they need to listen is this common network for these, how many, let's say 8 devices, is silent. So if everybody is always listening, if this medium is silent, then some of the device may start transmitting something. And if so-called collisions happen, so that 2 devices were start talking or sending the data at the same time, both are shutting up, wait for some random time, and then do it again. So what is good about star, the same as for token ring, that if something is broken in this cable, usually only this part of network is down. Not so good that you need more cables, and particularly of this Ethernet approach is that when network becomes more busy, then these collisions that 2 devices start sending their data at the same time becomes more and more frequent. So this means everybody is talking too much and nothing is actually sent. So you never can get actual utilization of entire time of this network close to 100%, because if it's close to 100%, then most of times many devices are talking at the same time, and so nobody actually receives normal signal anymore. But good thing about this star topology is that you can easily create network of networks. So you can make smaller stars and put them in larger stars together and put them larger stars together. And in most of cases, this is how entire internet is built together. So you have star of stars of stars of stars until you get to the backbone of the internet of large optical networks around the world. So more details about Ethernet. Protocol for Ethernet is called CSMA-CD, or Carrier Sense Collision Detection Protocol. And so what means carrier sense? All Ethernet devices are always listening to their channel, what is happening there. Why I'm talking about channel? Because the same principles what are true for Ethernet are true for wireless networks as well. And for wireless networks you do not have connected network, you have dedicated spectrum of electromagnetic waves somewhere around 2.4 or 4 point something gigahertz, where these Wi-Fi routers are communicating with other Wi-Fi devices. So everybody is always listening, and also checks that there is no collision. Collision means that more than one device is transmitting data. And if this collision happens, both devices or many devices abort transmission, and some may send jump signal, usually it is for wireless devices, and then they shut up for some random time, and this random time initially is shorter, and when they talk again, so time diagram should look like this. So here flows time, and here are, let's say, lifeline of 2 devices, device A and device B. And if it happens that 2 devices are sending the same time, they stop. And then both of these devices introduce some random time, how long they will wait, and if they are not lucky, they can try to retransmit data after the same amount of time again. So they then stop again, but if they got unsuccessful second time, this time between transmissions will be twice as large. And again, if they are not lucky and they start transmitting signal at the same time, then they back off or wait for 2 times more. So this is this exponential binary buck of time until sooner or later they should get such way that only one device is sending, so then this device finish their sending and other device gets successful. And of course, if there are many other devices here as well, then of course it becomes more and more complicated. And so then as more congested this channel, either switch or hub becomes, or Wi-Fi router, as slower this data transmission happens. And so here are more details about this Ethernet frame structure, which I showed you here. Some metadata about packet, how much data were sent, and also what is checksum for this data, and then MAC address of one device, MAC address to another device, etc. So, and at the end it may or may not have this cyclic redundancy check or control sum of all data sent here. So, and what is important particularly for Ethernet addresses is that initially this length of address was 48 bits. That is good, because when I will talk about Internet Protocol, which initial version which was released is only 32 bits, which is too small number. So this means that there is no much of problems to make this 48-bit field globally unique for different kind of devices. Now with virtual devices, etc., it may be a little bit of problem. Therefore, for newer Ethernet devices, this address field may actually be 64 bits long. But in most of cases, usually, it's still 48 bits. And then all Ethernet devices are listening all the time, and only difference is do they ignore these received Ethernet frames or not. And in most of cases they ignore everything what is not intended for them except broadcast address. So broadcast address is that you put 11111 in all these 48 or 64 bits. And they do this mask checking, this means that for any device with different actual address, all these bit fields which are needed will be filled up with 1. So this means all devices are actually receiving and handling these requests when somebody sends Ethernet frame where destination address is FFFF in hexadecimal or 1111 in binary. And also what may be is that for debugging purposes and diagnostic purposes you may switch your Ethernet device in so-called promiscuous mode when it actually provides to higher level of abstraction all Ethernet frames which it can receive. So because Ethernet is one common channel for several devices, for example here is some hub and many devices connected to this hub, and if one of these devices is promiscuous, then it can provide in higher levels of abstraction all these Ethernet frames which can actually be listened and received in this channel. So this means that you can also check and diagnose what one device was sending through the same channel from this device to that device, because of course this signal may be traveling also to all other devices, and so you can read data or receive data where some other devices are communicating through the same channel. So, and when you send data through the Ethernet, there is no any guarantees that intended device is actually receiving this Ethernet frame. So you just send it and see what happens. So that means if you need to have reliable data transmission using Ethernet on similar networks, you need to check it in higher level than just managing Ethernet network card. And that's what, for example, Internet Protocol does when it sends additional data inside this Ethernet frame. So it doesn't need any administration, you just connect your device to Ethernet network and it's done, and it becomes faster and faster. So in general, 99% of networked networks or wired networks in the world are Ethernet networks. There are still some other networks used, like ATM for bank machines, like SONET for optical network, but in most of cases, actual way how you send signals through some cable from place to place, de facto standard is Ethernet. And also what is interesting about Ethernet is that it has different physical connections which can you use with the same data handling approach. For example, there may be Ethernet network card which uses fiber optic and it uses light instead of electricity, and you may have Ethernet card which actually uses electricity or copper cables connected to them. And then you can put different Ethernet networks together. Maybe we will go in more details later, depending on how much time we have on other topics, how these are built. And particularly for wired networks, you can split your large Ethernet networks in parts using devices called switches. And what are repeaters, switches and routers? A repeater, there are almost no devices like repeaters in today's world because electronics become so cheap that a repeater is not used. So a repeater, if that was Ethernet network, just establishes electrical connection between different devices. So here you have these Ethernet devices connected to your actually hub. So it establishes proper electricity connection, and only thing why it's needed is because when you send here accelerated current through these wires, they behave like waves, and waves can reflect and go in unneeded directions, and therefore this hub establishes that this wave resistance for all connected cables is the same, that what actually happens that if one device is sending this signal, it nicely separates and goes till the end of all other devices, and then it dissipates, so it doesn't travel back and bounces forward and backward between these wires, just adding some noise. So anytime somebody sends this electricity signal, it goes in equal part in other end and then dissipates. So, and if you do not care so much about noise, then you can just put these Ethernet wires together without any hub at all, and it will work worse because this signal will bounce forward and backward, so it will be more noisy, but you can, in worst case scenarios, you can establish Ethernet network without hub at all. Then most of these hubs are actually switches, which is much more complicated device, and it actually splits communication from device to device using virtual channels. And for example, switch actually analyzes what is source and destination MAC address of particular Ethernet frame, and it checks that if this particular Ethernet frame is from MAC address 1 to MAC address 2, it actually sends this particular Ethernet frame from device connected with MAC address 1 to MAC address 2. And if it sees that some other Ethernet frame is sent from MAC address 3 to MAC address 4, it resends this Ethernet frame only to MAC address 4. And then, depending on how many connections it has in total and how many it has separate channels, actually, in this case, one device is talking, not all devices are listening, but only these devices are listening which are intended. And of course, if some of the devices sends broadcast signal, like this FFF or 111, then of course it resends this signal to every output here. So most of these devices, what we have at home office or work office, are actually at least switches. So they have separate internal virtual channels, and in most of cases only these devices are disturbed which actually need to listen this particular Ethernet frame sent from one place to another. Yeah, and what is repeater? Repeater is something like strengthening signal if you have very long Ethernet cable. For example, here is some device very far away from this hub, then you may have a repeater which retransmits this signal and makes it stronger to make it reliably received at the other end. And then talk is about routers. Routers are even more complicated devices because in switch, in hub, they do not care about actual data send at all, because it is just electrical connection, proper electrical connection between several devices. Switch has some internal complexity because switch actually reads data about source and destination MAC addresses for these Ethernet frames. But routers are more complicated, and routers work something like this. Here may be one of Ethernet segments, and here may be one of Ethernet segments, and some connection here, and one device may be sending Ethernet frame where important data is following. So here it's MAC address 1, let's say MAC address 2, IP address 1, IP address 2. So when it sends this data, Ethernet frame looks something like this. It sends from MAC address 1 to MAC address 2, and internal data is something like it sends from IP address 1 to IP address 2, and blah blah blah, something else. And router do not check only source and destination of MAC address, but it also cares about IP address or these data after Ethernet frame. And it checks, for example, is this IP address belongs to the same Ethernet segment, and if it is not, then what actually happens, somewhere may be some MAC address 3, MAC address 4, and it resends another Ethernet frame. So here is this Ethernet frame sent through this cable, but in this cable the data about Internet Protocol is the same. It says it sends from IP1 to IP2, blah blah blah. But about Ethernet frame, it says no, that source MAC address is MAC address 3 and target address is MAC address 4. So that Ethernet frame is sent here. So this is first and this is second. And then third, this router checks, for example, is this IP address actually available in this segment, and if it is, as in this particular case, then it sends another Ethernet frame with, let's say this will be the same MAC4. MAC4 is source and MAC2 is destination. And of course, regarding the Internet Protocol, data is the same, IP1, IP2, blah 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 blah. So, and this is what routers does. They resend new portion of this, and so this is 3 going through this wire somewhere here. They repeat information received from one Ethernet frame to other end to another to connect several segments of Ethernet networks together using Internet Protocol as this more general address space and data protocol how to send information from one place to another place. So, on key distinction. So routers are the most complicated ones and they retransmit Ethernet frames based on their IP headers. They check what is source IP address, what is target IP address, and then create new copies of these Ethernet frames to resend them in different Ethernet segments. Switches are more complicated ones because they actually can send these Ethernet frames only in these portions of network where it needs to be. They check what is this Ethernet target address of particular device. And bridges actually are something like repeaters, but difference is, I told you, that particularly for Ethernet, physical implementation may be different. And for example, if you have Wi-Fi, and here is your Wi-Fi router, and here is your computer, and it's too far away from this router, so signal is too weak, you can just add Wi-Fi repeater, which receives signal sent from your computer to this repeater and then resends it without any changes with better signal to make it work. And similarly, if you have Ethernet, wired Ethernet, again, if this cable is too long, you can add a repeater to make this signal stronger. But bridges do something like this. You have Wi-Fi here, and you have wired Ethernet here, and then you have this bridge which converts radio waves into electricity inside the wire. And if you have, for example, optics, then again it converts electricity into light. So everything may be the same, but it just changes medium how these data are sent through one place to another. So on hubs, these are the most primitive devices, and in most of cases you don't see real hubs anymore, but you may see repeaters and bridges, especially if you need to change medium how you send information from place to place. So, any questions or comments so far? Yeah, repeaters and range extenders devices are the same. You can call them repeater, range extender, something like this. They just receive chunk of signal and they retransmit this signal with more power to make it work. Any other questions or comments so far? If no, then we can go forward and now about DHCP, where P is protocol. What is problem? Problem is following, that there is now any problem to make computers work locally in local area network. You have either Wi-Fi or wired Ethernet and you connect devices to them and you can send Ethernet frames from one device to another device either using radio waves as for Wi-Fi or electricity through these copper cables. And good thing about this is that this device has its own MAC address, this device has its own MAC address, this device has its own MAC address, and this device. So you can send Ethernet frames from the place to place, so no need to configure anything. If we will have time, we will go in more details how this auto configuration work, and even if you have switch, which you usually have, it understands what MAC address these devices have, because first time they send something, so this switch here or on a device knows what MAC address is connected at other end of this cable or through this radio wave channel. But particularly for Internet protocol, it is not so easy, because initially Internet protocol had to be configured manually, and so this means that each of your devices actually has at least two different addresses. MAC address for Ethernet already been built into your network card by manufacturer, but IP address has to be assigned manually depending on your global and local network configuration. And so DHCP protocol is protocol which allows you to do auto configuration of connected devices, that these devices also get IP address, so that Internet protocol is used as a higher abstraction layer to send information in longer range than just locally reachable Ethernet network. And how does it work? It works in the following way, that in this case your Wi-Fi or Ethernet box is also a router, and it may be that this router also some another device connected to this switch, and this router should be also DHCP server. And usually if you get Wi-Fi router from some telecoms or other kind of router, usually this feature is built in, so they provide this service how this IP address can be assigned to all these devices connected to this particular Ethernet segment or Ethernet network. So idea is following, that some of these routers provide these DHCP services, and some of connected device may send Ethernet frame first asking who is DHCP server, and when this DHCP server is established, then this device sends another Ethernet frame and says please give me IP address and other needed configuration, and then this router gives it back to this device. So if you do not use DHCP protocol, you need to know, for example, what kind of IP address you need to assign to your computer, what is mask, which says how many bits of this internet address belongs to the network addressing, and how many bits, smaller bits, belongs to actual computers inside this network, and what is gateway or router, which retransmit your data if this particular IP address what you are sending is not reachable in local area network. But in DHCP, so device sends Ethernet frame with DHCP discover, which broadcasts. Then some of these DHCP servers, there may be more than one, sends offer back, and then it sends request to this particular DHCP server and gets some data back about IP configuration. So easier to see than tell. First we need to and then we connect to this back, and should be enough. And here are these Ethernet frames recorded regarding to DHCP protocol. So because Internet Protocol should be configured, but it can be configured automatically, so initially when this device is not connected to the network, it doesn't know about Internet Protocol configuration at all. So what it sends, it says that source, and here we see this regarding to IP protocol, but let's look in details about Ethernet. So when we look in Ethernet, we see that it created Ethernet frame and sent it. This is source MAC address, and destination MAC address is FFFF, so it sent everything. And it also sent IP data, so source address is all zeros, and destination address is all ones, or in decimal these are written as 255, 255, 255. So this is something, and then when you look here, it says my host name is following, something like please give me IP address. And then it received acknowledgement from this DHCP server. IP address for this DHCP server is 10.0.2.2 and destination address is 10.0.2.15. This is given address to this virtual computer here, and you see that here it sent back this to this particular network device with Ethernet address 080027 blah blah blah. So here you see the destination address is following, and so it says that your IP address should be 10.0.2.15, and it may also add different kind of information. For example, subnet mask is 255.255.0, that DHCP server is 10.0.2.2, and different kind of other information as well. And that's how you usually get your dynamic configuration for Internet Protocol. So now about sending a packet. On the same subnet, sending packet is very easy. You use MAC address of destination and you send to it. But in other subnets it may be different, and I will not go in details, but here again another protocol may be used where your device usually talks with this router and DHCP server it is address resolution protocol. And what it does, in general, it says, for example, what is MAC address for IP address, let's say 10.2.10. And so some of these devices says that MAC address for IP address 10.2.10 is, let's say, A, B, C, D, E, blah, 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 blah. So then it knows that if it is reachable locally, it sends from its source address, like MAC address 1, to ABCD, and IP address is its IP address to target IP address, blah, blah, blah. And in general, in simple networks, usually there is one MAC address related to one IP address, but it is only for simple cases, because there may be one MAC address and many IP addresses. For example, if you have router which connects several devices together, or you create a server which actually responds to many IP addresses, etc. And it may be that there are many MAC addresses and just one IP address. For example, if you do load balancing and you have several physical devices, farm of servers responding to the single IP address for load balancing, etc. And then what may happen is that when it asks about this, what MAC address is for this IP address, and it says there is no MAC address for this IP address because this IP address is not located in this local area network. So then you need to know MAC address of this router, which sends the same Ethernet frame again and again and again until your packet actually reaches a particular destination. And so this looks something like that. So here we have at least two different Ethernet segments, and IP address ranges for these two segments is something like 123 something for one segment of internet, and 567 something for other part of internet. And so if this host with IP address 123.48 wants to send something to address 1237, then only thing it needs to know is what is MAC address for this particular host. And of course it has its own MAC address, so then it can use Ethernet network to send Ethernet frame from this host to that host, and then it is reached. If, for example, it wants to send some data to address 5670, then it asks what is MAC address for this IP address 5670, and this DNS or DHCP server, so there may be many services located in the same box, says that it's not reachable locally, and you need to use routers. And router is, for example, with IP address 123.19. So what is happening first, that it now then checks what is MAC address for this router, and it sets Ethernet frame from this MAC address to that MAC address, but instead inside of this data it says that source IP address is 123.48, target address is 5670, and then this router similarly checks, can this IP address be reached locally? So does this IP address has Ethernet address or not? If it doesn't have Ethernet address, then it sends this data to the next router, and until finally this router checks what is, for example, address of 5670, what is MAC address for it, and then creates Ethernet frame, which sends from this MAC address to that MAC address to this IP address. But of course, source address was still this particular host. So that's what address resolution protocol does. And if we look on some example, let's start again. What we could do, let's not use browser. We will use IP address directly. Unfortunately, it was cached, and this device already knows what addresses are reachable and what are not. So it didn't record that part. So where we create some break. Any questions, comments so far? Let's talk about this and then we will create some break. So now about IP addressing. So IP address for Internet Protocol version 4, which is most widely used, is just binary 32-bit number. And usually these 32 bits are grouped into 4 octets or 4 bytes, and values historically are represented not in hexadecimal number but in decimal number system. So this means minimum for each of these octets or bytes is 0 and maximum is 255. And then this addressing system is hierarchical. Internet consists of networks connected to networks and then actual hosts or final devices, and older bits or larger bits of this address are used to address what is network inside network or network connected to network, and then smaller bit shows what is actual device connected to this internet network, and so this is called this bit mask. But initially this bit mask was hard-coded and it had 3 different levels. Either only first 8 bits represents network and all 3 remaining bits represents many devices connected to them. So that means there could be only 255 different networks, and 2 in power of 24 is, I think, 16 millions. Here it is, 16 millions of computers connected to this network. Or if you can choose that first 20 bits are network and remaining 22 bits are, 12 bits are computers, then you have 2 in power of 20, I don't know, few millions of networks and approximately 1 million devices connected to it. Or first 16 bits means network and remaining 16 bits means device. Then you have 55,000 of networks and 55 devices connected to these networks. But this initial approach, when internet became larger, was too rigid and it didn't work well because splitting address part between network and device was two large steps, and therefore later so-called hierarchical address allocation was invented, where you actually add additional information about this mask, how many bits represents network and how many bits represents devices connected to this network. So this means you can put particular split between networks and devices depending on how many networks you have and how many devices you have connected to this network depending on your needs. And so this dynamic approach is now used everywhere, but because of historical reasons, you still may see that some of these address ranges in local area networks are more widely used than others. For example, you may see network addresses starting with 10, and this is inherited from these A-classes networks when first 8 bits means addresses of network and all other bits means addresses of hosts connected to this network. Or you may see 172, for example, if these first 20 bits are network and then all other are computers or concrete devices. 192, for example, if first 24 bits, I think, and 2024, 2014. So there are still some remains about preferred address ranges for local area networks, what kind of first number here is for network because of this classed addressing system. For example, if I check what is address for this virtual machine, you see again, so its address starts with 10, not with something else. So there are still places where you can see, and what is important here when you look on these address ranges is that these address ranges which start with these specific numbers, initially these were intended only for data transmission using internet protocol in local area networks. So that means that if you had some particular device and it wanted to use internet protocol and its address started with 10 or 172 or 192 or whatever, these were all local area network addresses, and initially these were intended that you can use them inside your own organization to use internet protocol between several Ethernet networks, but still inside one local area network inside in your organization. And sometimes these are called these metropolitan networks, something bigger than just one segment of Ethernet, but something like that. But I think after break I will, and so that means that if you wanted to use a wide area network, your device actually also should have another IP address which doesn't start with these numbers, so non-local, like 24 or 68 or 100, I do not know. By the way, 127. Yeah, everything which starts with 127 is virtual address which is called localhost. It is a virtual IP address where you can check connectivity of your computer itself. So if you check connectivity on localhost, you actually check, for example, is internet working for my particular device. But because of some thing called NAT, network address translation, and I will tell you later why it was introduced, now you can actually send data to the public network also using private address space, which is pretty bad because it adds complexity, but unfortunately that's how things work. So, any questions or comments so far before we take a break? I take that as no. Before we go forward, what I wanted to show is how this address resolution protocol works. And it's still no cigar. Oh, yeah, finally. So, to make things faster, when particular device needs to resolve link between IP address and MAC address, or Internet Protocol address and Ethernet Protocol address, it caches or makes local copy of information for all these data. But when it doesn't know anything, here how it looks, for example, for some of these data. So if it needs to send some information to IP address and there is no link already known what MAC address this IP address has, then it sends yet another Ethernet frame here, which here says who has IP address 10.0.2.2, and then somebody answered that IP address 10.0.2.2 MAC address or Ethernet address is 52.54.00.12 blah blah blah. And when we check, for example, we see that following links between IP addresses and Ethernet addresses are already known for this particular machine. So, now about Devil invented to deal with Internet Protocol version 4 bad features. And what are these bad features for Internet Protocol version 4 is that lengths of bits what you can use to address specific devices are only 32, and 2 in power of 32 is approximately 4 billion, or very precisely 2 in power of 32. And 4 billion may sound quite large number, but it's not large number at all when you have many millions and maybe even billions devices connected to the internet. So it's not enough. And because of that, Internet Protocol version 6 was invented, and its address space is 128 bits, or 2 in power of 128, which is billions of billions of billions of billions, but it is not so widely used as it should, because computer scientists invented Devil called network address translation. And what does it mean? In general, it means following: that if you have host using Internet Protocol version 4 and you give some IP packet to the NAT device, after some time this NAT device says that not you created this IP packet, but this NAT device made this packet. How it works in details? It works in details following: that when you look on entire address space, here and all these things, there are different kind of windows reserved only for local area connections. And if we show them something on number axis, so here is 0 and here is 2 in power of 32. Everything is public except some particular ranges. Somewhere here is 127 something, somewhere here is 192 something, somewhere here is 10 something, this is larger. Somewhere here is, let's say, 2 in power of 32, which is reserved for something. So, and everything else may be public addresses. And originally, for device to be connected to the internet and use internet, source address should be from this public space. Let's say this address and target should be in public space. And these addresses were only for local communication between these, so there could be many local area networks which uses the same address spaces, but they do not disturb each other because they are not using it for internet. But there is not enough address spaces for Internet Protocol 4 to all of these devices which are using internet to give their own another public address to be connected from one to another. So what do they use? They use some of these local area connections addresses and they transform it or translate to one single public IP address like this. And from internet perspective, there could be networks of networks of networks, all which starts with 10 blah 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 something. But from internet perspective, all this communication goes only through this address, let's say, I don't know, 85 blah 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 something. And that's what IP addresses, not devices does. So here is one of public IP addresses, here is cloud of internet, and here are some clients which are using actually local area network addresses. So you cannot send data from this address to this server and back because routers do not send packets where target destination is intended only for local area. So routers just ignore these packets if they are sent by mistake. But what this NAT address may do is that it translates this internal IP address to some public address and then it's sent to the internet. And because there may be many clients and they may not be imaginative enough, and another number which is used to distinguish particular connection is not only source and destination address, but so-called source and destination port number, and this is 2 in power of 16 or approximately 65,000 different ports. For example, destination port 80 is HTTP server. So it also checks that a particular set of these translated addresses do not overlap, that this NAT device actually knows that when it changes these ports back, that it should be sent to this particular client, not this client. And so then the server thinks that it sends this address to some public address, but it is translated back to actual address. So here, actually this was not about NAT, but this is. So here we have local area addresses starting with 992. And this device sends packet to publicly available server to port number 80, and it is imaginative port like just any free port which can be developed. And this NAT device changes this internal IP address to externally available public address, and it remembers that when it will receive packet block to IP address 1234, port number 2000, then it needs to retranslate it back to 192.234.1001. So there should be table, because otherwise it will not know how this duplicate of packet and changed packet needs to be sent back to this computer, not to that computer or something else. So on what this server receives is completely valid Internet Protocol packet, public address here, port number here to receive, port number here to send back, and it sends response from his IP address to that IP address, from his port to that port, and then this network address translation converts it back to this internal IP address to this internal port here. And because this network address translation device needs to remember these tables, how these internal addresses should be and port numbers should be translated to public IP addresses, and this memory to remember this table is not infinite, then sooner or later it may happen that this response do not go back to your device, because this address table is, or translation table is full. What do? You create new connection, and in most of cases it works. And sometimes if your NAT device is especially stupid, usually you find out that your router needs to be restarted at least once a week or once a day, somewhere in night, whatever. And most of cases why it happens is because its translation table is overfilled and it cannot to do this translation anymore. And so if here you see that this device was not imaginative enough, it also uses port number 1001 and port number 80 to the same server. Now it needs to change this port number to something else, because otherwise this network translation will not go properly, because response will be to this address. If this same port will be used for this device and that, then this NAT device will not know how to translate packets back to either this computer or that computer. So it adds another translation rule in its table. This server still thinks that only communication is happening between this server and this NAT device. But what actually happens is that in this particular case, two different computers are sharing the same public IP address between them. And that's one of the reasons why you, for example, check what is IP address for your computer. You see here that this computer actually has internal IP address starting with 10, so it cannot talk to the internet without network address translation. And because of that you see that this address for this particular computer is following, but if you open some service, it is following. So this particular computer, and I can show, for example, my physical computer here. So for this physical computer, its address is 10.0.0.11, but if I check for my physical computer, what is my IP? You see that my physical computer and this virtual computer shares the same public IP address, and later I will show you that there actually may be NAT devices behind NAT devices behind NAT devices behind NAT devices. And that also is one of security vulnerabilities, because some of these devices which are hiding behind this public IP address, there may be some Russian or Chinese computer hackers which actually try to break something for government institutions, etc. So that's a problem. And so parallel, all modern devices today can use two different Internet protocols in parallel: Internet Protocol version 4 and Internet Protocol version 6. There are quite a lot of changes between these two protocols, and you may think about these two versions of protocol like English and French. Writing is similar, many things are similar, but of course these are two different languages. And similarly, Internet Protocol version 4 and version 6 are different languages. Basic principles are the same, but the most important part about Internet Protocol version 6 is that address space, what is reserved for IP addresses for these devices, is 128 bits. And it is not enough to give unique address for each atom in the universe, but it is quite enough to give unique address for each atom in solar system. So this address space is much larger, and because of that, network address translation is not allowed. So if your device can talk both Internet Protocol version 4 and version 6, you see something like this, that Internet Protocol version 4 address is following and Internet Protocol version 6 address is following. But in this particular case, again, there are some address spaces which are intended only for this local area communications. And if you see Internet Protocol 6 address starting with FA80, and here it's written in hexadecimal number, and two colons here means many zeros padded in between. So last bits in hexadecimal means FA80, many zeros in between, and then this number. So this address is intended only for local area communication. So my computer here cannot talk with Internet Protocol version 6 globally. But if I go to website server, what I see here is that for Internet Protocol version 4, again, it has another local Internet Protocol version 4 IP address. For example, if I check what is public IP address for this server, it is 52.58.11.108. But what server sees internally is that its address is again local area address, so there is network address translation happening on the other end. So network address translations may be in two different ends. Source network address translation is about your home or office network, where there are many devices behind one single network address translation device. But in other end, called DNAT, there may be again just one single IP address. So here is public address and here is public address. There may be several devices hiding behind it, like Odo.lv server. So again, here it has internal address, but it's translated to public address, and there may be many devices actually sharing the same public IP address for different servers. So this is destination network address translation. And sometimes these local area addresses, which also are translated to public address, are called demilitarized zone, DMZ. This means some of these addresses through the translation are actually reachable through the global area network or internet. And so here I see that for this remote server, it has two different Internet Protocol 6 addresses. One is still locally reachable, so you can use like dash interface. Don't remember. Capital E. So I can use this particular address in the same local area network to use, but this other IP address, that is global IPv6 address for this server. For example, or so this is, and this for this computer to work globally using Internet Protocol version 6, it has to have address which is reachable globally and globally unique. So no network address translation is allowed for Internet Protocol version 6. So most widely you can see addresses starting with FE80. This is something like 10 something 182 something 172 something. These are only local addresses. And then there are some address compatibility layer between Internet Protocol 4 and 6. But so if you see something like this, then you should know that your computer actually can't work with Internet Protocol 6 version globally. Now about domain naming system. So what is DNS? DNS is service which allows you to convert names into IP addresses. For example, when we open website www.cnn.com, or shorter could be something like this. Okay. So before actually opening this website, odo.lv, what is happening is that computer actually asks what is address for domain name odo.lv, and so it creates. And this information, what is domain name server for this particular computer, it is usually given by DHCP protocol, this dynamic host configuration protocol. So it asks to local DNS server what is IP address for odo.lv, and it gets response that IP address for odo.lv is following. this answer here. 52, 58, 11, 118. So that's what DNS actually does. How it actually works. DNS system should be organized because all these names should be globally unique, at least to be used globally again inside organizations, similarly as you can use your own address space for internet addresses, which overlaps with other local addresses with different local networks. Similarly, you may use the same domain name system with overlapping names inside your organization and other organization. But of course, when you talk about entire internet, these names should be globally unique. So that means you need to have some kind of hierarchy. And this hierarchy is not done in centralized way, because if there would be one super duper DNS server which knows everything about internet, then it would be narrow place, an attack place or attack vector, as they say, that it will be abused. So there are very many different levels of domain name system servers organized in a following way. That first, there are different organizations which organizes different subdomains, and for some historical strange reasons, most parent ones in domain name system are to the left and not so parent ones to the right. So in normal, so it is little endian system, so small numbers are in beginning and large numbers or names are at the end. Why it happened, I do not know. And so there are different organizations which actually organizes particular tree of registry for these particular subdomains. So usually each of government institutions for each particular country have their own domain name system, and these are so-called root servers. So, and what is important here is about organization level and query level. For example, in organization level, LV, LT, EE, COM are all different organizations which organizes this domain system into IP addresses and back. But of course you can register domain without assigning IP address to it yet, just to put your foot into this address space. So these are more or less independent, like pyramids for these particular things. But then problem happens is if you don't know anything about DNS, where you start, and this is about changes or modification. So there are many small pyramids which allows to do changes in each particular area. For example, here is .lv, here is .lt, here is .ee, here is something like org, etc. But then there are copies created from these called authoritative services. Which are authorities for each particular namespace here. But then there are global servers which creates copies of these pyramids, which you can use as a primary DNS server to ask for some data. And long time ago, these addresses were quite hard to remember. But for example, one you can always start is 88888, which is Google, or 8844, which is also Google, 1111, which is Cloudflare, and quite other. So you can start querying everything about anything from these servers, but they are not authorities, for example, for .lv. What they are doing, they are creating cached copies from .lv into their system. And then, if you run your own Office suite, etc., you can create your own small copy in your home office. And then your DNS server may be like 10.0.0.10. And again, it's not authoritative because it may create copies either from these global ones or other ones, but it will be good enough for your particular reason. So what here is important to remember that they are authoritative servers, and authoritative servers are these who allow us to do changes for particular namespace. Each country has one, each large organization has one, etc. And they are querying services which you can start using if you don't know any other DNS server than these global ones, like coming from Google, coming from IBM and Microsoft or whatever. And then you can create local cached copies for yourself. How does it look on practice? On practice it looks following, that here is nits.lv website where I can change my data regarding to odo.lv domain. So I open nits.lv and I can put what, for example, IP addresses are for these host names, etc. And then what happens is something like this. And as lookup is utility to check what is IP address for domain name system. And I can write odo.lv. And what I see here is that my computer actually has its own local DNS server, because IP address for this server is 127, which means it is localhost. So all Linux computers today have their own, and this is not inside virtual machine, it's inside my physical computer. So today, because DNS server is not very resource hungry, usually I don't know about BSD and MacOS and other Unixes, but Linux-based operating systems have their own local DNS server locally. But what we see here, it is not authoritative answer, so this means it is cached copy of IP addresses for this name, but this server, in this case 127 blah blah blah, is just some random server, in this case on my computer, which just happens to know what IP address for this name is. And similarly, you can do something like this. You can say server is, let's say, 1111. This is Cloudflare server. And you query it, and it now I have queried this server, and it still says it's not authoritative answer because it is just cached copy of these global servers. So who is authoritative answer? We can use utility called dig, I think. No, who is? So name servers for odo.lv are actually these ones. And I say server should be this one. And now I check what is odo.lv. I see, here now it's authoritative answer. Because actual knowledge about odo.lv or .lv domains in general comes from these two domain name servers. So these are authoritative for this particular domain, and every other server just creates copies of this database to make things faster and more robust. So read-write permissions comes from authoritative servers, these ones, but then everybody who is not lazy can create copies of these DNS records, and then everybody who is not lazy, including your own computer, may create its own domain name system locally, copying this data from other things. So this is good in terms of robustness, because there always should be some DNS server available to resolve names into IP addresses. What is not so good is, and then how it works. So you can create different servers. One is recursive and another is iterative. Recursive is, for example, that your local server knows, for example, these root DNS servers and some of these top-level domain DNS servers. So root servers are these well-known IP addresses where you can always ask something like for 8s for Google, for 1s for Cloudflare, etc. Top-level domain DNS servers are these which are actually allowed to change data for a particular subdomain. And then your server may ask this server, that server, that server, etc. So that's how usually real servers work when you put dedicated DNS server in your office. On your local computer, it usually does following. It just asks something to the next server, and it asks something like this: do whatever you need to do until you know what name is, what IP address is for this name. So it may do something like this. I have my local DNS server on my computer, but it is recursive. So if it doesn't know what auto.lv is, it just asks to next one. And next one is probably my home router. And it is also recursive. Maybe it knows because it can create a copy of this information. If it doesn't know, it asks to somebody else. If it's connected through the LMT or TET or whatever, these may be some domain servers in LMT, TET, or these telecoms. And if they don't know this, then go up until they reach some of these global servers coming from different organizations, and then they respond back to this server, to that server, to that server, till to my local computer. So that's how it works. What is not so good about these things is that there is no any security added when you actually decide is this record broken or not. And they create local copies not only to resolved names to addresses, but also negative ones. For example, if you ask something like then it creates local copy that there is no IP address for domain blah blah blah, and every next time I'm asking, it actually do not ask this recursively till to these servers which know something about this domain, but it just immediately returns no IP address for this particular domain. And so good thing is that every time you create these copies, it works pretty well, because every time you open some website, you send email, etc., you always need to know what actual IP address is, and if everything would be centralized, it would be bottleneck. What is not so good is about security, because if you want to open, let's say, Microsoft.com, okay. Let's try it. So this is additional good about these web certificates. We will talk about this in details later. But anytime you can hack this DNS server, you can actually get wrong data what IP address for this particular domain name is. So that's one of this main problem about DNS service, how you can deal with this. One thing is what was introduced in protocol called DNSSEC or Secure DNS, which means that you add signature to your response. And about signatures we will talk in details when we talk about security, but idea is that these responses are signed from these DNS servers, and you can check that it is not altered during transmission. For example, when you do this recursive search from server to server to server to server, here is my local server, here is my router, here is my telecom, and here is, let's say, Google. So Google might sign its response, and then if somebody wants to change that IP address for Microsoft.com is actually different, then of course this signature will not be valid anymore. And so all these servers in the between, if they just resend this information back till to my computer, then I will see of course that signature do not match actual data. But it still doesn't deal with this problem that somebody may hijack some DNS server in between and it can actually sign invalid responses, and then of course you will still have this problem. And other important part is that of course today many care about privacy and many do not care about privacy. And problem is that these who provide you DNS service, they actually know quite a lot of metadata what you are looking at, because if you do something like and when you do this query, then all these servers which actually responded what IP address for this domain is actually probably knows that I am interested about this particular domain. So you can know quite a lot of, I do not know, some different names, and everybody who is between your DNS query, and that will actually know that you are opening this particular website. So what can you do? You can encrypt these data, that these who are in between and transmit your response back, they encrypt these data. So what they see is that some encrypted data are sent, some blah 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 blah, sent from this DNS to that, and then some blah 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 is sent back, but they do not know was it odo.lv or something else. And this protocol is called DNS over TLS, Transport Layer Security. So everybody knows that client is talking with this DNS server, but everybody else do not know what exactly domain was asked for and what exact IP address was responded back. Another approach is DNS over QUIC, which is introduced by Google, but most widely what can be used is DNS over HTTP protocol, actually HTTPS. So, and it is also implemented in most of modern web browsers. How does it work? It works in the following way, that usually when you open a website, let's say Okay, I can. Oh, I think I recorded it here. So before I open website odo.lv, what actually is happening, I'm asking some server what IP address for domain odo.lv is. But if you enable this DNS over HTTPS, let's fix this bug. Otherwise we may be surprised. And now we see something more appropriate. So we can do following, that here how to search for that, maybe here. Connection settings. Here. So here, your browser, you can activate DNS queries over HTTPS protocol. And if we enable it, and then we start recording it. So what we see here in between is that first encrypted connection, transport layer security version 1.2, was created with this IP address, and I believe this is address of this Cloudflare DNS server. And so some data were sent to this server, some data were received back, but these were encrypted and nobody actually knows what DNS record I was asking for. Of course, this target server still knows that I was interested about this particular domain, but if you are using some other DNS server which provides this service, like PLAGoods custom IP address, then of course they will not know about which particular domain names I was interested about. So that's one thing you should remember when you want to be whistleblower or something about this, related to this. And let's check how much time we have. I think we can talk about that. Yeah. So that's about DNS protocol. And now finally for this day's session about ICMP protocol, or Internet Connection Message Protocol. What this protocol is, it is just sending IP packets wrapped into Ethernet frames to ask something for some address and get some response back. Something like request response. What you can request. You can, for example, request something like please respond. That would be echo response requests. You can do other things, but in most of cases you usually do check, for example, does somebody respond to something or not. So how do you do this? Utilities which are using ECNP protocol are most widely used is ping. And ping does following. First, let's check. And what it does is following. It sends Internet Control Message Protocol packet from this address to that address. And here it says something like with its type here, type 8, which means please respond. And then you get answer back that this server is responding with type 0, this is a reply, and you get some data back. So it is used to check connectivity, and you can do it in two different ways. If you ping particular IP address, of course you are sending this ECNP packet directly to this IP address, but if you are pinging by domain name, then of course what you are actually doing, you are checking two different things. First, that DNS protocol is working, some DNS server is responding to you, what IP address for this target host is, and then you are sending these ECNP or echo request packets to this IP address and back. So if something doesn't work for you properly, remember that it may happen that actually DNS protocol or resolving from names to IP addresses is not working. So that means you should know at least a few IP addresses to check. And if you do not know anything, then you can ping these global root servers for DNS like ping 1111 or ping 8888 and check that you get response back. So that's one thing. Other thing what you can do is, for example, check how fast your network is. Then you need to be root user or administrative user to this. You can say something like ping flash okay, let's check what is IP routes. Flash. This means send packets as fast as possible to this router. And it increases this number of dots if number of sent packets is bigger than number of received packets. And then we can check, for example, how quickly it works, and 0 packets are lost. Sooner or later we can get some other, and here I think I wrote the wrong address, so nothing was sent back, 100% packets lost. And then for example, I can also send packets as fast as possible to some remote server, and then I see that it works far slower and some of packets are actually lost. And there are other options. But what is very interesting and important is a utility called traceroute. At first, let's see. And how this utility works? It works similarly to ping, but with more iterations. So ping means please respond, and here is my computer, and here is target computer like odo.lv. And here are many routers in between, because there are many subnetworks between my computer and that target computer. And if I send ping, so it immediately does something like this. So source address for this computer was something like then 0 to 15. And for odo.lv it is so it sends packet immediately, so source address is this address, target address is this address, and what actually happens is that many routers resend many Ethernet frames with the same IP data. Source address is this, target address is that, please respond, and then when it sends back, it says source address is this, target address is this, and sends back. But with traceroute, it adds additional thing here. It also says please respond, but it adds so flag time to leave with different numbers 1, 2, 3, 4, 5, 7, etc. And what happens is that if this time to leave is 1, and routers always decrease time to leave number for these packets by 1 for each next hop when they send this packet to different network, is that when this router receives packet, it reads it and it sounds something like this. My source address is 10.0.2.15, target address is 52, 58, 11, 108. Please respond, but time to leave is 1. So it should retransmit it to the next, but because it decreases it to 0, it do not resend it anymore because it is dead. Why? Such thing is introduced because in large networks you can misconfigure networks that packets are going into infinite loop. So, and to not allow them to go into infinite loop, such time to leave is introduced. So, and if this router is nice, it sends something back, something like this. Your stupid packet request from here to here actually died here, and my IP address is blah blah blah. Then it increased time to leave to 2, and then this router sent his attitude or viedoklis back about this packet, etc., etc. But not all routers are nice. For example, here I see that I got response from this router, which is internal IP address, so it is first hop. Then here is another router, still internal IP address, and got response back. So here we are going into public space, public IP addresses, router in between, 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 and stars here. So somewhere here we got some router which didn't care to respond back when this packet died, and it is encouraged that routers respond, but because this is one of performance reasons, that if your routers is abused and it is too busy just responding to these died packets, it may not respond. So somewhere here I think we are in internal network of Amazon. Again, we see many routers do not respond at all, and so finally here we see that Odo server responded back. So somewhere here, and for example, if we say and we see, for example, that Microsoft decided that many of their final routers do not respond about died packets. So it ended up here B is out response. But if routers are nice, and most of routers are nice, here you can see what are routers in between your computer and remote computer. So that's what I showed here. That's how it looks like. Demonstration. And then there may be that when you connect network to network, maximum amount of data what you can send in one single chunk is different. Especially it is for different kind of old telecom networks like DSL, etc. And then you get something like fragmentation of packets. You send one single larger packet initially here, but then somewhere in between this packet is split in smaller parts because so many data cannot be fit into one single packet. So this is packet fragmentation. And then at the other end they are assembled back, if everything works successfully, into one large request. In Internet Protocol version 6, packet fragmentation is not allowed because this is another security issue. But that means every client which first sends some data to the server needs to know what maximum transmission unit is between this computer and that. So how can you do it? You can do like this. What was size? Size. S. Just one. So you got response back. Do not fragment also should be added. I think. Let's check it out. I don't remember. This switch. So, and if we do not allow fragmentation, I can check that actually such large packet cannot be sent between my computer and that computer. But for example, this big goes through nicely. And then if Internet Protocol 6 is working on your computer, then there is utility like ping 6, I don't know. And in this case, Internet Protocol version 6 is used to encapsulate data and do something like this, or also you can say ping-6. It is also another possibility. So that's about the introduction to the networks. Any questions or comments? Definitely last session will be much more philosophical, but it still will be technical, because with my as I told you, when different teachers present different courses, they always add their own personality into actual implementation of general agenda. And because I'm not so experienced to look on the social behaviors, how technologies shape society and how it changes, therefore I think I can't add much and contribute much in your knowledge regarding to this area. So I think that in most of cases we will mostly talk about all these things from technical point of view, not from social or any other things. But yeah, technologies shape society, and then of course we can talk about, for example, how Facebook has changed the new generation and maybe current generation, and how Google has changed things that now youngsters do not try to remember technicalities and trivialities because they just Google for these things. So, but yeah, I can't contribute much to your knowledge regarding to such aspects, and I am not absolutely sure what end of series for these lectures will be. I'm pretty sure what will be last lecture. So maybe if I will come up with good ideas what I can present to you, then I will show it to you. But I think that in most of cases I will touch more technical things. Any other questions or comments? Start recording. So for this second homework, one of things I thought you could do is, for example, to do some automation to easily create folder inside folder inside folder for this exercise. And I came up with this, and I checked also what my problem was. If I put it in script, you need to double escape these variables like %% instead of %. But we can open command window. And we paste it. And it works pretty good until we reach folder, in this particular case F60. Why? Because file name is or extension is too long. When Windows NT was introduced, I think it was in 1995, in parallel with Windows 95, it introduced new file system called NTFS, and NT means new technology file system, and so they were very proud that instead of DOS convention, 3 letters for file name, 3 letters for extension, you could use up to 255 letters for name of the file. But it was actually a little bit lie, because it was still limit that also when you refer to this file by full path starting from root section of your file system, like C:\\, blah 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 blah, this path also couldn't be only 255 characters long. So this means if you have short folders inside folders inside folders, then your name to the file could be longer. If folder inside folder is also quite long, you can't refer to this file anymore, because total full path of this folder cannot be more than 255 characters. And as we can see, nothing has changed during these 25 years, so no any extensions. And I didn't know this because I have not used Microsoft Windows regularly for quite long time. So, and I thought that with this script everything is done. So what can you do? Of course you can create 2 separate folders, then create another folder starting from F61, and then somehow put this and update it inside your zip archive. In theory you can somehow come around it, but it is not so easy. But looking in future, and I think this future will come in next session when I will tell you what your homework will be regarding to networking, I thought that maybe it's easier for you to use external service and use some properly built operating system to come up with solution for this exercise, because changing rules during game of course is bad, and if I would change something, then of course I would discourage these guys who already, at least they think, they have completed this exercise. So I never try to discourage or make additional problems for these who work timely. So, what can you do? You can use external service and connect to remote server tools.odo.lv, which is Linux server provided to you for your different works. How you can connect to it? First, you need to download a utility called Strange. Putty. Maybe I have copied this link incorrectly. Let's check it out. Okay, I'll just paste it and double check it later. So you download this utility, which is used to create remote connection to remote Unix-like system server from Microsoft Windows, and there are many installations. One is installer and another is just executable file like putty.exe. If you are using computer from your employer and you do not have administrative privileges, you are not allowed to install anything, then you just download this file and execute it. But if you want to update also your start menu, etc., then you use installer, and I think that for my virtual Windows this should work. Why it doesn't work? And another utility is Midnight Commander. For Windows, hopefully this link will work. So what means this? Add to pass and add desktop shortcut. Desktop shortcut is adding shortcut in my desktop, but adding to pass means that if I open command window, I can also open it in following way, writing MC. So, and why are these used? Putty is to create a remote connection to remote server. Where it is, not putty gen, putty, this one. So, and you write tools.lv. You can save it for future things. And one, if you will work regularly with putty, it doesn't use nice looking fonts by default. You can change for this session that fonts would be different. And so you log into this computer. with username and password coming from this thing, but it was arts and rtc blah blah blah. Where is this putty window? And then you have created remote connection to this remote server. You can also open Midnight Commander there as well. If you don't know much about Midnight Commander, so it's pseudo-graphic commander which shows you two current folders in two different screens. You can navigate through these folders using Enter key and arrow keys, and you can do different other options what are written here, like help, menu, view, edit, copy, make, delete. So these are functional keys: F1, F2, F3, F4, F5. Here of course you have problem with Mac users because for modern Macs they do not have functional keys anymore. And so you can do everything there, but of course here you have only text interface, so you can't do that part regarding to the documents, but you can copy some documents. But here you can very easily create folder inside folder just with this command here. And here it is. But then you need to copy some local files to this remote, for example, to create this zip archive with this command here. And here this Midnight Commander comes in. And you can use also Midnight Commander as a file manager not only on your local file systems, but also on remote file systems. Don't I have anything created there? Maybe I deleted. Ah, that's not that. Let's check, do we have somewhere? Okay, we have something here. And here you press F9, which is pull down menu. Then activate, for example, right here, and you can create secure FTP link to remote server. And here you write like arts @tools @lv. Write password RTC702. Okay. Let's do this, let's say. Actually, maybe it's easier first to move it just in your home folder. Let's here put, let's say, this file on the remote computer. And this file. And then with PuTTY, you see here we have these files created, and then let's say remove this folder here, open Midnight Commander, Ctrl-O to hide these windows and C command line. So you can do it in different ways. For me, that would be easy in following. Create these many folders inside folders inside folders. Open back in Midnight Commander and we see the current folder is F100 here. Copy these files which you need to put inside this folder inside folder inside folder, and then create archive. And then copy it back to your local computer. And here it is, and if you open it with like 7-zip archivator, you'll see that this archive is created. So, because everybody of you will be using the same username and password, it may be that here you see some kind of like garbage or whatever, you may reuse it, but what will happen is that every night, I do not know, at 3 or 4 o'clock, all these additional unneeded folders will be deleted. So, if you are lucky, you may see something left from previous students. Then of course you need to check that what you see there is what you actually need. But if you think this is too extra effort, if you will learn this, then security exercise, which I will explain in next week, will be a little bit easier to you. And here I'm actually deleting it in the wrong way. I'm actually deleting all these folders from my local computer through this remote file system. It was not the most efficient way how to do these things. So you should learn something about Midnight Commander, and you should learn how you can connect to a remote server using SSH protocol, which for Microsoft Windows users this is. And then you exit out of Midnight Commander pressing F10 functional key. And then I don't need to change rules during game, and it is still technically possible for you to complete this exercise.